this video, we would like to introduce a new design of angle-insensitive, reconfigurable intelligent surface, RIS. So far, RIS have received a lot of attention in communication community due to their ability to manipulate the characteristics of electromagnetic waves such as amplitude, phase, frequency, polarization, and propagation direction. However, some researches reveal that the M responses of RIS are sensitive to the incident angle, which will cause angular reciprocity and lead to uplink and downlink misalignment in wireless communication. Here we propose a novel 3-bit RIS element with angular insensitivity at normal and oblique incidence. To meet the phase requirement of 3-bit RIS, we use a vector-loaded meta-atom to precisely control the reflection phase by controlling the biasing voltage. To solve the problem of angular sensitivity, we introduce metallic vias between adjacent elements in order to restrain the multiple reflections from the inherent layers within single element, and stabilize the coupling between neighboring elements. Both the simulation and measurement results show that the amplitude and phase responses of the proposed RIS are stable under TM incidence from 0 degree to 60 degree. For comparison, the same element without the metallic vias is also investigated from the spatial dispersion curve. It can be found that the phase deviation is greatly suppressed with the change of the incident angle and the presence of the metallic vias. To demonstrate the beam steering capability of the proposed RIS, the reflected angles for TM wave incident from 30 degree to 150 degree are evaluated. To verify the angular reciprocities of the proposed RIS, 2 experiments are performed. In the first experiments, the incident angle is set as 90 degree, and the angle of the main reflected beam is 112.5 degree. Next, the incident wave angle is set as 112.5 degree, and the main beam is reflected back to 90.5 degree. In the second experiments, the main reflected beam is 58 degree, when the incident wave angle is 150 degree. Also, when the incident wave angle is 58 degree, the reflected beam is 146.3 degree. Due to the angle-insensitive meta-atom design, the angular reciprocity can be maintained at the normal and oblique incidence. For more details, please refer to our published paper. Thanks for your attentions.
Hello, my name is Denis Nikolaev. I'm researcher and project leader on wireless bioelectronics at the ITR laboratory of the French National Center for Scientific Research. I'll overview our paper on the reconfigurable antennas for in-body bioelectronics, but first, big thanks to the APS Society and Dr. Marco Sallucci for the opportunity to feature our research here. Our main motivation is to enable the new generation of miniature bioelectronics that can offer powerful biosensing and therapeutic capabilities. These devices require efficient and robust wireless operation to ensure safe and reliable link, high data rates, and low power budgets. However, a typical efficiency of an antenna radiating from a lossy human body is below 1%. It strongly depends on the implantation depth and operating frequency. Moreover, the position and orientation of the device are hard to control and can account for up to 10 dB variation in path loss. In this context, we developed a new antenna that responds to these challenges. It consists of an array of 2 dual-band conformal microstrip elements, and to keep the implementation as simple as possible, we used a single fit with a single switch to reconfigure the radiation patterns in both bands. For the lower band, the elevation pattern is dipole-like and the null vector can be rotated for about 15 degrees. At 245 GHz, the rotation is about 20 degrees. The combined gain has no deep nulls for both operating frequencies. As for the impedance characteristics, the antenna shows a single resonant frequency around the 434 MHz and a double resonance around 2.45 GHz. The antenna performs very well in any water-based tissues for both bands, and it has a reasonably good characteristics in fat tissues as well. Finally, a few words about the radiation efficiency. Note that the computed values strongly depend on how the body tissues are modeled and also on the position, size, and the type of the antenna. It is very difficult to decorrelate the intrinsic antenna radiation from the phantom, and a direct comparison of the gain with counterparts, as we see in many papers, should be taken with care. One solution to see how efficient an in-body antenna is to gauge it by the maximum achievable radiation efficiency of an equivalent source in the same reference phantom. You can read more about this approach in this work. This plot compares the antenna performance to the fundamental limitations of electric and magnetic equivalent sources. For more technical details and explanations of this and other topics, I invite you to take a look into the full paper. And also do not hesitate to contact me by mail for any question. Thank you for listening.
Hi everyone, this video briefly introduces frequency reconfigurable smart antenna with integrated electroactive polymer for far-field communication. Ionic polymer metal composite, also known as IPMC, is a type of electroactive polymer. IPMC generally fabricated using nephew membrane and plated with metal electrodes such as silver on its surface. There are several excellent features possessed by IPMC, including low attraction voltage, light weight, fast response, and most importantly, it can be cut into any sizes, even in micro size, without losing its attraction properties. For the first time, the IPMC attractor is integrated with a RFID tag antenna for achieving frequency reconfiguration in the ultra-high frequency band. The tag antenna comprises a planar squaring patch that is coupled with an IPMC movable flat attractor. Based on the simulated current distributed animation, the squaring patch serves as the radiator while the IPMC attractor serves as tuner. Therefore, the frequency of the tag antenna can be reconfigured correspondingly with the deflection of the IPMC attractor. Here is the frequency reconfiguration demonstration of the IPMC integrated RFID tag antenna in an ionic chamber. Initially, when the IPMC attractor is at rest mode, the resonant frequency of the tag antenna is at 0.92 GHz. When the IPMC activated and deflected in outward direction, the frequency is tuned up to 0.93 GHz. Similarly, when the IPMC activated again and deflected in downward direction, the frequency is tuned down to 0.89 GHz. This shows that our frequency reconfiguration tag antenna can possess 2-degree frequency tuning features. The IPMC integrated RFID tag antenna also tested in an open-air environment to simulate the real-life operating condition with a commercialized RFID reader. The tag antenna is located on 3 different packing objects, which is metal, artificial skin, and alkali plate. For all cases, the divided resonant frequency of the tag antenna can be tuned back to approximately 0.92 GHz with a significant improvement in the read distance. Lastly, this is the summary of this video. We invite you to check out our paper published in IEEE Translation on Antenna and Propagation for further detailed justification and explanation. Thanks for watching this video.